Yes, thank you for coming. And my name is Johannßen from Hamburg, and it's a pleasure to be here to talk about my current research. It's called Knowledge Sharing for Robots via Cloud Computing, and I want to talk about how to connect the robot now with the cloud and how to share knowledge between the robots. So let's start. I want to talk about firstly why more and more researchers are interested in working on this topic. I want to present the topic Cloud Robotics. I want to give you a little bit insight into my current research, and finally I want to end my talk with a conclusion and the references. So, the internet has become one of the most important communication media, and we are sharing information every day, every time, and we help each other through the internet. So, and if you are working with robots, you see that they are very limited in many ways, like cost, hardware resources, local knowledge. They are not able to help each other. They are not able to share experience and information through each other. So it would be nice to use the internet to solve this problem. And the precondition to do this is already done. Robots are Wi-Fi enabled. They have abstract interfaces with mostly great software developer kits. And yes, what does it mean, cloud robotics? It means the separation of the physical components and the software components of a robot. The physical components like actuators, sensors, cameras, speakers are still on the robot, but the software, the brain of the robot, is outsourced in the cloud. So you can use this approach, in my opinion, for two things. Robots are able to share knowledge about objects, description and models like a chair or a table. They can share plans like sets a table or whatever, and they can share information about environments through each other. So, and the second point is that if a robot doesn't provide many computation power, they can outsource heavy tasks like speech recognition or object recognition in the cloud. And yes, we see this in the figure, that we are able to share information about heterogeneous robots. So, this idea is not new, to connect robots with remote server. Masayuki Inaba from Tokyo has already researched it at the beginning of the 19th. So, his idea was to equip the robot without a brain. He wanted to provide image processing for little or small mechanical animals. And these mechanical animals didn't provide much computation power. So his idea was to offload the task image processing to a remote server. So these small animals are able to send the image to the remote servers, and the computation will be done from the cloud, and it receives the result. And this was the first idea, and now we are able to transfer huge amount of data through the network, and that's very fast. And now we can see, with the aid of cloud robotics, we are able to improve the learning mechanism of the robots, because they are not longer on their own, and they can benefit from the experience of others. So what does it mean? If a robot gets something new knowledge, it can share it with other robots via the cloud, like handling a task in an unknown environment, or they can share executable plans. That doesn't mean if a robot learns a task and then he can translate it to a more abstraction format and can upload it in the cloud, and if another robot has to do the same task, he can download this information and solve it. So that's the idea, and that gives us many opportunities. And the second one is, I have already said it, we are able to offload compute-intensive tasks in the cloud, and a robot can access a web service, for example, for massively parallel computation on demand. And the last point is very important, I think. With this approach, we can build lighter, cheaper, and smarter robots, because we are not able to provide to equip a robot with much computation power and not much hardware resources. That's very nice, I think. So, I want to show you some projects with knowledge sharing for robots. The first one is RoboEarth. It's from many universities, and this presents a World Wide Web for robots. A robot can share information about plans, actions, environments in the cloud, and another robot can download it. So it's a kind of web service to store robotics-specific information. And the second one, RoboEarth is one of the mainly components in my current research, so I want to speak about it later in the next chapter. Robot Share is not longer active, but the idea is very nice. It provides a search engine for robots. So the idea was, if a robot doesn't know how to wash cookware, for example, it can access this search engine, like Google, for solving this task. So it can ask it, and it receives a URL reference to the knowledge. But this knowledge isn't executable. So it wasn't a good idea, but it's not longer active, this project. The next projects are involved in outsourcing heavy tasks. These projects are the target of the project is to provide platform as a service to outsource robotic algorithms like path planning, SLAM, simultaneous localization and mapping. And RoboEarth is a project from RoboEarth team as well. And this team provides a platform as a service. They provide path planning and reasoning algorithm in the cloud, and a robot can access this engine for computation in the cloud. And DaVinci is a project which provides algorithm like path planning and recognition and something else. This project implemented this algorithm with very efficiently methods like MapReduce, if you know. That's for parallelizing robotic algorithm. So if a robot aren't able to do it locally to solve a task, he can access the cloud, and the cloud infrastructure has many computation power. The third one is from Google. They are providing a web service to get the right grasping strategy for the robots. So if a robot is in front of an object and it doesn't know how to grasp it, it can ask the web service to find the right strategy. And the last one is a perfect example for to build cheaper robots and lighter robots. It's Romo from Robotics, a smartphone robot. You only need to have a smartphone, and you download the app from Romo. And this robot is using the hardware components and the computation power of the smartphone. So it's very nice. And for $99, it's very cheap. And yes, that's some projects. So we want to go into my current research. My target is to connect the Now robot with the cloud to provide changing of executable plans among several Now robots. And I will reach this target with the aid of RoboEarth, with this storage of robot-specific knowledge. So the idea is, if Now is learning new stuff, maybe he's solving a labyrinth, and he finds the shortest way, he can translate this plan in a more abstraction level, and then he can share it with other Now robots through RoboEarth. So he can upload this plan into the cloud, and another robot which is still in front of the labyrinth and it doesn't know how to solve it, he can download this shortest way, and then he can go through it very easy. That's the idea. And that's the process of the RoboEarth. If a robot wants to have an abstract a plan like serve a drink, he can access RoboEarth. This request is going to the execution engine, and this creates a product query. Product is a programming language which provides a semantic mechanism to access RoboEarth. It delegates this query to NoRob, and NoRob scans the database of the RoboEarth database for the given plan. So the RoboEarth database stores information about actions, plans, objects, and their relation between each other. And it receives the abstract plan for serve a drink. Then NoRob provides matching between the capabilities of the robot against the requirements of the plan, because not every robot are able to solve every problem. That's true. And if success, NoRob sends this abstract plan, which is defined in the OVL, in the Ontology Web language, which is like XML, very abstract. So NoRob sends this abstract plan to the execution engine, and we need executable formats. So the execution engine translates this abstract plan to the cognitive robotic abstract machine plan language, which is an extension of the programming language Lisp. And this method we can use this language for defining abstract plans, and then we can access the process modules of the robot. This provides the interface to the hardware components of the robot, and then we can access the interface and we can execute the plan on the robot. So let's see the architecture. This is the architecture of my laptop. If a robot wants to access the RoboEarth database, he has to access firstly my laptop, and then he can access the RoboEarth database. So on the top of Ubuntu, I have installed the robotic operating system. It's an abstraction layer over the robotic specific hardware. So, and this is very modular, and you can install modules. It's called stacks, like for NoRob, RoboEarth, the Now wrapper. The Now wrapper presents a library which wraps the library of the Naoki SDK. So you can control the Now robot with ROS commands on a more abstraction layer. You can say to the Now, move from A to B, but you don't have to think about it, how he solves this problem. So we have stacks for RoboEarth as well, and NoRob, and the plan language as well. And I have said the RoboEarth database stores plans in the Ontology Web language, and this is an example for abstract plan, like serve a drink. It contains some dependencies for bottle, bed, and cabinet, and it includes some subplans. For firstly, the robot has to move to the bottle, then it has to grasp the bottle, it has to move the bottle to the bed, and then you put it on the bed. And that's an abstract plan. And the next step is to translate this abstract plan to the CRAM plan language, the Cognitive Robotic Abstraction Machine language. And NoRob sends, with the aid of NoRob, we are able to send a semantic query, like for serve a drink, to the RoboEarth database, and it scans the database and it receives the given plan, and then it translates this abstract plan to the Cognitive Robotic Abstract Machine plan. And this plan is like a top level plan with designators, which provides the metadata, like the bottle is type of a drinking bottle, the bed is type of a furniture, and that's a very, very abstract plan language. It provides the opportunity to execute the same plan on different robots, and that's very nice, and that's why I use this cognitive robotic abstract machine language for my project, and that's very cool. And yeah, that's my global architecture. So if you now want to share information, like uploading, downloading information to RoboEarth, you have to access this component on the laptop. You can install ROS on the now directly as well, but that's but this approach is more secure. And yes, okay. So I'm now implementing the interface between the now robot and the RoboEarth database, and we have already saw that RoboEarth provides process modules, and every robot which wants to share knowledge via RoboEarth has to provide a process module, and the process module represents the interface through the RoboEarth database and the hardware components of the robot. So we have to map this the abstract plan, like grass a bottle, from the gram plan language to the more now specific commands to execute it. The target is that we want to execute an abstract plan on the now. So we have to map this language to this language, and then we can execute abstract plans on the now. And that would be very nice, I think. And that's the point where I'm currently working on it. Then I want to execute some scenarios, like if now has to perform a task which it hasn't performed before. It has to scanning the database for the given plan via NoRob, and then NoRob translate this abstract plan to the gram plan language, and then the now can solving an unknown task. And this is a scenario which I want to execute in the next time, and it would be very cool if that is success. So, technical challenges, we have a lot of technical challenges. The first step of my project is to provide a knowledge sharing between homogeneous now robots. Next step is to provide a knowledge sharing between heterogeneous robots, and that would be more difficult because they have different capabilities, and we need an abstraction layer, which we have. We have the robotic operation system, which is the abstraction layer over the different robot properties and hardware components. So that's already done. But we have, it's very, very difficult to perform the same task on different robots. It's a very big challenge, but I want to go solve this challenge maybe in later time. The third one is latency problems, because we have connection through the internet, through the cloud, so real-time processing is not so easy. So we have latency problems. The other thing is we have outsourced the cloud as the brain of the robot in the cloud. So we have the problem if the connection is dead, so the robot became brainless, and that's a problem. But we can provide a local small brain on the now robot that he can use basic functions maybe. Yeah, last one is we have security problems. If you want to provide, or if you want to have many robots in a hospital, for example, and they want to share plans or information about patients, so the question is register information about your patients in the cloud, and what will happen if the cloud is hacked. So you have such security problems, and we have to think about it. And yes, that's it. So finally, what we have talked about, I have presented the topic cloud robotics, which presents separation of the physical components and the software components. We can share information about plans, environments, actions, objects through this approach, and we can offload heavy tasks to the cloud if a robot doesn't provide much computation power. We are able to build cheaper, smarter robots. We have seen many projects which are currently working in this topic, and I think this approach has many advantages and opportunities, but many risks and problems as well. And we have seen insight into my current research, where I'm trying to connect now with the RoboEarth database. I'm using the middleware ROS, is the abstraction layer over the robotics-specific hardware components, and I'm using the CRAN-plan language for defining abstract plans to execute it on different robots. And NoRob, it's the components which is for reasoning and for scanning the database for a given plan. So I want to end my talk, and thank you for your attention, and yes, thank you very much.